The convolution operator is defined as an integral between functions. So the convolution of f and g is f star g, a new function. And since it's a function, I have to tell you what value it gives to a particular x. And so the idea is that the convolution of f and g at x, the value of it is the integral of f of y times g of x minus y dy. So this is the cross correlation of f of x and g of minus x. And so it has a number of interesting properties. And these properties mainly just boil straight out of its definition as an integral. So first off, it's commutative. So it turns out by a simple u substitution that it doesn't matter which order you write the arguments in. F star g equals g star f. It's also associative. And so this can be proved with Fubini's theorem. It's a bit obnoxious to write down because you got to deal with the iterated integral and coming up with some decent symbols for all the dummy variables and whatever. But it turns out it doesn't matter what order you evaluate the convolutions in, it comes out the same. Now secondly, if I got the integral of c times f, times g, then I can put the constant next to f, or I can put the constant next to g, or since it's a constant, I can pull it out of the integral altogether, and it doesn't matter where it is. Okay. Also, it distributes over addition. So f star sum is the same as f star g plus f star h. That again, straight from the basic integral properties. So these two together I'm going to refer to as linearity, because their linearity of the operation g goes to f star g. Okay, so we can think of the convolution as a binary operation that takes two functions and makes a new function out of it. We can also think of it as an operator that takes one function to another. So just by itself, as a binary operation, the convolution is a lot like the usual notion of multiplication. Multiplication. So the usual notion of multiplication, which is piecewise multiplication, so the product of f and g at x is usually just defined to be f of x times g of x without any fancy integral business. All right, so this is called pointwise. I will distinguish by calling it pointwise multiplication. So, for example, what happens with a Dirac delta? So if we look at the convolution of delta with f, well, at the point x, this is going to be given by the integral delta y f of x minus y dy. And what does delta do? Well, by definition, it evaluates where its argument, which is y, because we're integrating with respect to dy, where y is equal to 0. And so if I look at this term here where y is equal to 0, I just get f of x. And so from leftmost to rightmost, this tells me that the convolution of the Dirac delta against f is just f itself. And by commutativity, we have that it goes both ways. So I'm going to call this property number 5 in my list, and it is the identity property. So in other words, for this new notion of multiplication, delta acts like the multiplicative identity 1 does for pointwise multiplication. So the Dirac delta is our new version of 1. And then we have the sixth property, which I'm going to call the magic property, because of the amazing things you can do with it. And that is that if you look at the derivative of a convolution, then this is the derivative of f convolved with g, or f convolved with the derivative of g. And so this is amazing for a bunch of reasons. For one thing, suppose that g is not differentiable. Suppose that it's not even continuous. Well, if f is nice and smooth, so say g is nasty. G is like ching, 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 nasty, discontinuous, whatever, ugly function. And suppose f is some nice function, maybe like a bell curve or something, so that it's, say, as differentiable as you want, infinitely differentiable. Well, then if you look at f star g, it's going to be as differentiable as either of its arguments, because I can use the magic property to put all the derivatives on f, for example. So as soon as you have a convolution with a smooth function, the result is going to be a smooth function. So convolution against f is a smoothing operation. And so it's used a lot of times in applied contexts, in neural networks and image processing and whatever else. You convolve your signal against a smooth function, and then you get something that's nicer, blurred out, smoothed off, something like that, easier to deal with. But for our purposes, we're going to be looking at differential equations. So say L is a differential operator. Like say L is partial with respect to t minus k times second partial with respect to x, or something like that. So that if we apply L to u, we would end up with u sub t minus k u sub xx, the heat operator. Okay, so then L of a convolution is going to be, well, I can put L by linearity and the magic property together on either of the arguments that I want to. Now that's really cool, because we can combine all of this stuff we have and make a great savings out of it. So suppose you want to solve some non-homogeneous PDE. So we want to solve this guy right here. And as a first step, we find W such that L of W is the Dirac delta. Okay, well, if we've got that guy, then we're done. We automatically know that W convolve F will solve our PDE. And you say, wait a minute, how does that work? Well, let's check. So how will we check? Apply L to W star F. So if we look at L of W star F, then by the magic property, we can put L wherever we want. So I'm going to put it on W. And then we know that W is a solution of LU equals delta. So this is going to be delta. That's how we defined W in the first part. And then we saw above that the Dirac delta is an identity for convolutions. So that just gives us F again. Okay, so from left to right, we see that since L of the convolution of W and F is equal to F, if we put U equal to this convolution, it will solve the PDE. Okay, and that's what makes it so useful. So we call W a fundamental solution. Once you found it, you can solve any non-homogeneous PDE. It's also called a Green's function. And so in an engineering or physical context, this non-homogeneous function here, the L part corresponds to the system, the device that you've built, whatever, and then this F right here corresponds to the forcing function, the influence of the external world acting on the system. And so what this is saying is, once you know how the system responds to a unit impulse, a Dirac mass, then you can use this convolution to figure out how it's going to respond to any external impulse no matter what. And this is called Duhamel's principle, and we'll look at it in an upcoming section.